The last application that we're going to be discussing for trigonometry deals with a new type of coordinate system called the polar coordinate system. Now, throughout this course and throughout pretty much every course that you've taken in mathematics, you've dealt with what we call the rectangular coordinate system with an x and y axis. Okay, it's also called the Cartesian coordinate system after René Descartes, who was a French mathematician who designed that, but we'll call it the rectangular coordinate system. Well, a polar coordinate system basically uses different values to identify points on a plane. Let me give you an example with rectangular coordinates. In rectangular coordinates, you have an x, y point, xy ordered pair. And that ordered pair corresponds to the horizontal and vertical positions of that point. Okay? The x value being the horizontal and the y value being the vertical. Okay? What's nice about rectangular coordinates is that every point has a unique identification, and every identification has a unique point. So if I give you the point 2, 3, you know exactly where that is. If I plot the point on here, if I plot a point, you can uniquely identify the ordered pair for that point. With polar coordinates, instead of having an xy combination for your ordered pair, you're going to have a radius and an angle, r and theta, as your ordered pair. Okay? So rectangular coordinates are x, y. Polar coordinates will be in the form r comma theta. Okay? Now, with ordered pairs, you want to have the potential for any real number to be in the coordinates there, right? So for x and y, you have all real numbers for x and for y as possible values. Same for r and theta. Now, you might ask, well, how do you get negative values for r? We know r can be 0 or positive. Well, we're going to allow r to be negative as well, a negative radius. Seems a little bit strange, but for instance, if you had a 30-degree angle but a negative radius, a positive radius would go in the same direction as the angle. A negative radius would go 180 degrees the other way. Okay, so if you had a 30-degree angle with a -2 radius, it would be out in the third quadrant at a, it would be equivalent to a 210-degree angle. Okay, so we can have positive, negative, 0 radius. Same with theta. Theta can be positive values, and we know what positive angles are. They're angles that go around counterclockwise. Negative angles would, of course, go around clockwise. And of course, they can be big angles, they can be small angles. You can have angles that exceed 360 if you keep going around the circle. You can have angles that are negative and even farther away from 0 than -360. Just depends on how many times around the circle. And as a result, you don't quite have the unique identification with polar coordinates as you do with rectangular. Right? So with rectangular, I said for every point on the graph, you have a unique ordered pair, and for every ordered pair, you have a unique point. With polar coordinates, that's not quite the case. Every ordered pair will have a unique point on the graph, but every point on the graph will end up having an infinite number of possible ordered pairs depending upon how many times around the circle you're going, or whether you're using the positive or the negative radius. Okay, so there's not quite the one-to-one correspondence between the geometrical point and the ordered pair as you have with the as you would with rectangular coordinates. It is a slight downfall, but it has its perks as well. Okay, so now if you had a point in rectangular form, you could always turn it into polar form, and vice versa, using trigonometry, using all the trigonometric relationships that you would that you've seen now with vectors and with complex numbers. Specifically, we would say that r squared is equal to x squared plus y squared. That's your Pythagorean theorem, essentially. We also know that the tangent of theta is going to be y over x. We also know that x is equal to r cos theta and y is equal to r sine theta. Okay, and we've seen these similar relationships with, again, complex numbers and with vectors in the past, but now we can apply those to polar coordinates. Technically, polar coordinates don't really have an xy axis on them. Instead, the polar coordinates have what we call a pole, that's the origin essentially, and a ray that comes out from the pole that gives you the angle of the point. We call it the polar axis, is the polar axis and the pole. So the pole, oops, sorry, spelled that wrong. I wrote polar, not pole. The pole is essentially the origin, and the polar axis would correspond to what we refer to as the positive x-axis on a rectangular coordinate system. Okay, so your pole is the origin here, and the polar axis is your x-axis, your positive x-axis. And then everything gets measured off of those two things. So your radii are the distance to the pole, and the angle is your angle off of the polar axis. Okay. Okay. So now we can do some converting. We can do some identifying of points. What's very nice about polar coordinates is that you can write complicated equations in more simple ways. Anytime you have, say, an x squared plus y squared in an equation, you can just replace it with r squared, for instance. So there's nice ways to simplify things. We'll get to that later. For right now, we'll just look at converting coordinates of points. So if I had, for instance, the point in rectangular form of 2, 5, that's in rectangular form. If I wanted to convert that into polar form, well, again, there's an infinite number of different polar ordered pairs that would work. I'm just going to use one with a positive radius and an angle between 0 and 360, but then I can vary that as well. So I'll show you how that works. So from 2, 5, if I want to find r, I know that r would then be the square root of the sum of the squares, 4 plus 25, which would be the square root of 29. Okay, so I have a square root of 29 for my radius, and then the theta would be the inverse tangent of y over x. The inverse tangent of 5/2, I'm going to need a approximation for that. It's about 68.2 degrees. Okay, so this is an approximation. All right, so it's an approximation. Tough to get a precision on these without the points being on one of our nice triangles. You could just leave it as inverse tan of 5/2 if you were actually looking for the exact value, but I'm going to be okay with some rounding on these, and I believe my math lab will as well. So we'll say 68.2 degrees for the angle. Okay, so that's the polar form. Now again, this is polar form with two conditions. One of them is that the radius is greater than 0. The other one is that theta is between 0 and 360. Okay. However, those don't have to be the case. We can have negative radius. So let's say for a moment, now, if I were to sketch this out, the point at 2, 5 over here has a radius or distance to 0 of square root 29. This angle is our 68.2 degrees. Well, if I wanted to call that a negative angle, Okay, let's consider a negative angle. I would need the angle to be down here into the third quadrant. Okay, ooh, that's not a straight line. In fact, none of this is straight very, very well. There, that's better. So I would need to go with a, let's see, 180 plus 68.2. That's a 248.2 degree angle. Nope. So that's 248.2 degree angle. So that gives you the angle down in the third quadrant. And then negative radii take you back into the first quadrant. Okay. So to get that same point, you could do a negative root 29 with a 248.2 degree angle. Okay. Okay. Then from these 2 points, and again, they're 2 different ways to represent the same point on the plane. From those, you can get an infinite number of other points. So this first one here, every time you add or subtract 360, you get another way to represent the same point. Same thing here. Every time you add or subtract 360, you get a coterminal angle, and that would be another way to represent the same point. Okay. So there's an infinite number of points that correspond to, or infinite number of ordered pairs that correspond to the same point. Okay. Okay. We can also think about, instead of having like a rectangular grid to find our values or to find our points, we often plot these with a what I would call a polar grid. Your rectangular grid would have an XY axis, and then every unit or every so far you would have vertical and horizontal lines to represent your values, right? Your X and Y values going across. So this would be what a rectangular grid would look like. A polar grid, instead of fixing a horizontal and vertical direction, you fix a radius, and then you have sort of concentric circles building out. So a polar grid, oh, you know what? It's better to draw the circles first. Imagine these actually being concentric circles. A polar grid would look something more like this, where each concentric circle is at a fixed increasing radius. Okay, so maybe a radius of 1, then 2, then 3, then 4, then 5, and so forth. Okay, so your polar grid will look like concentric circles rather than a bunch of perpendicular intersecting roadways or something. And so then you can have fixed angles going out. You could have like your 45-degree angle in all directions. And then you could have maybe your 30-degree angles and your 60-degree angles. It's going to look a little bit like your unit circle, but with more circles. Okay, so there, it's going to look something like that. So there's our polar grid. Okay. And of course, the intersection then, if I wanted a point here, this point might be, let's see, 1, 2, 3, 4. That's 5 circles out. So there might be a radius of 5 at an angle of 30 degrees or something like that. Okay, so we can identify points that way using concentric circles for fixed radii, and then your angles as kind of rays shooting out from the origin, or from the pole, I suppose we should say.